Welcome back to Arxflix. Today, we're diving into a novel paper titled DiLoCo, Distributed Low Communication Training of Language Models. This research introduces a groundbreaking method to train large language models efficiently across poorly connected clusters. So, let's break down the main components and findings of DiLoCo. Take a look at this illustration. DiLo leverages a distributed approach inspired by federated learning, where several clusters of devices, known as islands, independently train model replicas on their local data for numerous steps before synchronizing. Standard training of large language models requires high bandwidth connectivity among thousands of devices, all housed in the same location. This setup is logistically challenging and prone to failure if even one device malfunctions. Traditional setups also struggle to leverage heterogeneous devices efficiently. DiLoCo aims to circumvent these issues by allowing independent training on smaller, loosely connected clusters. Inspired by federated averaging, DiLoCo optimally combines local and global optimization steps. The inner optimizer is Atom, while the outer optimizer employs Nesterov momentum. DiLoCo significantly reduces communication overhead. Contrary to traditional methods that require constant communication, DiLoCo communicates only after hundreds or even thousands of local training steps. This low communication strategy allows the use of devices in different locations and diverse computational environments efficiently without hampering performance. The experiments on the CFR dataset reveal that DiLoCo, using only 8 workers, achieves comparable or even superior performance to fully synchronous setups while communicating 500 times less. This figure illustrates how DiLoCo outperforms a baseline model and matches the performance of models using significantly more resources. DiLoCo shows robustness to various data distributions and can handle resource availability fluctuations seamlessly. These properties make it well-suited for real-world applications where computational resources are inconsistent and heterogeneously distributed. There are 2 main optimization processes in DiLoCo: inner and outer. Inner optimization happens locally on each worker for multiple steps, while the outer optimization synchronizes the model replicas across the workers. This equation shows the inner optimization process. The workers update their local parameters using the Atom optimizer. For the outer optimization, Nesterov momentum is applied to the averaged gradients from each worker, updating the global parameters, which are then redistributed to the workers. The robustness of DiLoCo is further underlined by its performance across different settings, such as varying the communication frequency and dealing with asynchronous communication. Experiments show that even with reduced communication and network failures, DiLoCo maintains strong generalization performance. This figure highlights DiLoCo adaptability. Training performance remains consistent regardless of how compute resources are allocated over time. This feature is particularly advantageous in environments with fluctuating availability of computational resources. DiLoCo presents a compelling solution for distributed training of large-scale language models. By significantly reducing communication needs, it enables efficient use of heterogeneous and geographically dispersed computational resources. This innovation is a step forward in scalable and resilient model training, opening new avenues for leveraging distributed infrastructures. Thanks for tuning in to Arxflix. If you found this summary insightful, make sure to like, subscribe, and hit the bell icon to stay updated with the latest in AI research. See you next time. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.